Okay, we're back again, and now I'm going to give the word to Levi Jamt from DNV GL, who will present the OSP software.
Thank you, Lars. Let me share my screen. Here we go. Yes, my name is Levi Jamt, and I've been leading the software development in the OSP project. On a daily basis, I work with the research and development at DNV GL in Trondheim. And today I will give a practical introduction to the OSP software by running live demonstrations. And I hope to give a taste of what the OSP tools can do, and maybe also make you curious about how it can be useful for you. For developers, we have created the libcosim, which is a C++ library that enables co-simulation orchestration. It supports FMI
Levi?
version. Yeah.
Sorry, I can't see your screen.
Oh, that's weird. Let's come again. Let me try again. Thanks for notifying.
There
Is
we
it
go.
Good now?
Yes.
All right. Sorry for that. So that's the libcosim supporting version 1 and 2 of FMI, and systems to be simulated can be configured using the OSP-IS that Martin just demonstrated, or a companion standard to FMI named SSP. Some of the features libcosim offers are running scenarios, distributed simulations, real-time or free-running modes, exporting results to files, and allowing models to communicate at different timescales. We also have developed a C and Java wrapper, which are helpful for developers who want to use libcosim in other languages than C++. Based on libcosim, we have developed 2 applications for running co-simulations: the Cosim demo application and a command line interface. The Cosim demo app offers a graphical user interface for easy exploration of the libcosim features already mentioned, and it includes plotting functionality and real-time inspections of the results. For non-developers, this is the recommended starting point for exploring OSP. With a command line interface, you run pre-configured simulations from the command line. It also includes features for inspecting, testing, and debugging models. OSP Maritime Reference Models is a collection of simulation models delivered as examples on typical maritime equipment, such as thruster, crane, hull, winch, power plant, sensor, environmental loads, control systems, and also models for communicating with real non-simulated systems. All models demonstrate the use of OSP-IS and are also put into a context and used in larger system configurations. The purpose of this collection is to provide examples that are useful when getting started with the interface specification and running simulations with OSP. Next, we have the OSP validator, which is used to validate that models and configurations are correct with respect to the OSP interface specification. And you have already seen that one demonstrated by Martin. Finally, we have a couple. This is a graphical drag and drop configuration tool to create simulation setups. Couple targets to ease the process of connecting simulation models and creating full system configurations. It can also validate the configuration, run simulations, and plot the results. So now it's demo time, and I will use the mass spring damper case that Martin just created. And the focus will be on showing OSP features rather than analyzing the system. We start with having a look at the Cosim demo application. So in this directory, I have downloaded and unzipped the Cosim demo application. And by running this run Windows batch file, it will start the application and launch the user interface in your default browser. Here, in the configuration input field, we type in the path to the configuration we want to load. And as we want to use the configuration for that Martin created, I have that one located right here. It contains the damper, mass, and spring FMUs, and the corresponding OSP model description files that we had a look at, in addition to the OSP system structure file. So we copy this path and paste it into the configuration field. In the log output field, you type in the path where you want the results to appear. So let's have a subfolder called results, and we load the simulation. Here on the simulation status page, you have some controls at the bottom that allows you to control the speed of the simulation with respect to real time. So if I enable the real time target and set the real time factor target to 3, this means that the simulation will execute 3 times faster than real time. And clicking play in the top right corner, you see simulation time progressing, and it is 3 times faster than real time. When disabling the real time target, the simulation will execute as fast as my hardware allows. And in this case, approximately 60 times real time. For now, we'll first reset the simulation, which will bring the simulation back to its initial state. And for now, we'll leave the real-time target with factor 1, which means that we will simulate in close to real time. To the left, you see the models. We have the damper, mass, and spring. Clicking on this allows you to monitor the simulation values. They are organized with tabs for inputs, parameters, and outputs. And to the top left, you see the plotting section. We can create time series plots and XY plots, which are scatter plots. Say you want to visualize the position of the mass to get a better trajectory of a better view of its trajectory, then we'll need a XY plot. And we can give it a name. As position. Now we need to add the X position of the mass to the X axis of the plot. So we go to the mass and find its output, and should mention that we would like to organize these variables using variable groups. That is still on the backlog, as the variable groups of OSP interface specification was settled rather late in the project. So for now, you don't have the variable groups presented in this demo application. But I know that the output out LU is the x coordinate of the mass. So I add that to the mass position x-axis. And the out LW is the y coordinate of the mass. So I add that and connect that to the y-axis of the mass position. Now we have the plot set up, and I will click Save Plots Config, meaning that we don't need to set up this plot the next time we load the project. So let's reset the simulation and watch the mass from the beginning. Okay, the spring and damper are attached with one end in the origin and the other end to the mass. And the initial position of the mass is right here at the x5, y0. And we see here how the gravity pulls the mass down and the spring force that pulls the mass towards the origin, and that the damper which slows the motion down. Let me also demonstrate the time series plot. So we are interested in seeing how the mass velocity develops over time. And I click Add Time Series. And also give this one a name. Mass velocity. And then we add the velocities in x and y direction to this plot. That is out FU. Add the plot for the out FW as well. So that's the velocities in x and y direction. Again, I will save the plot and can reset, start from the beginning, and have a look at the velocities. Yeah, so here we see how the velocity in x and y direction are developing over time. These plotting features are nice to have when we explore systems and they are presenting results. However, the simulation results are also available as raw CSV files. Remember, we defined the results directory as a subfolder in the configuration. And we can have a look. So here's the configuration. And there we have the results folder. Looking inside, we see there are multiple CSV files. For each simulation run, that's created one CSV file for each model, logging all variables for each time step. And we can open one of them. So this is the results for one of the mass simulations we just did. The first column contains the simulation time. The second contains the step count. And then all inputs, outputs, and parameters are logged in separate columns. In some cases, you want all variables like this. In other cases, that is not necessary. That's why we have enabled a way to pick the variables you want to log. You do that with a XML file named logconfig. And I have prepared one here, logconfig XML. There's a root element called simulators. And within this one, we list all simulation models we want variables from. Here we have a list of 2 simulation models. We now want the variables from mass and spring. And for each model, you specify the variables to log using variable elements like this. In this case, I log 2 variables from each of the models. If you don't need values for every single time step, you can use the decimation factor attribute. Here I've set the decimation factor to 3 for the spring model, which means that its values will be logged every third time step. Now let's see how this works. Here's my configuration folder, and we place the log config file we just looked at into this folder, and we can just delete the previous results. We reset the simulation and run it again. Going back to the results directory now, we see that we only got results for mass and spring, as the log config did not include the damper. And opening the mass results, we only find the two. Oh, okay, just let me. It's hanging on the application. You can open it again now. Here, I will see that we only log the 2 variables that we specified for the mass. And these are actually the X and Y coordinates. So if I quickly insert a plot, we should recognize the pattern from what we saw inside the plotting functionality inside the demo application. Next feature I would like to demonstrate is variable overriding. So let's start the simulation. Any variable can be overridden by clicking the edit icon next to the variables. This is a handy feature for exploring and tuning your simulation case. Let's say that right now our mass model suddenly loses half of its weight. Makes no sense, but we can override this mass to from 10 to 5. This, and maybe the spring malfunctions and gets a lot stiffer. We can go into the spring stiffness and increase it from 5 to 15. Like that, and having a look at the velocities, we now see that the velocity got affected from the changes that I just did here, reducing the mass, and here making the spring stiffer. So these are nice features for exploring the system at hand and manually creating scenarios. However, if you would like a scenario that easily can be repeated, we support specifying scenarios in JSON files. And here I have an example. Demo scenario.json. You give your scenario a description, and then you specify a set of events. An event is defined by selecting relevant variables by the relevant variable by specifying the model and variable. Then you specify the action. Here I've used override. And when overriding, you must provide the value you want to set the variable to. And you specify at what simulation time you want this event to happen. This way you can build up a scenario with a series of events to take place at specific points in time. And this example right here does what I just did manually. At 10 seconds, I set the mass of the mass to 5, and this at 20 seconds, the spring stiffness is overridden to 15. For the scenario files to be picked up, they must be located in the configuration folder within a subfolder called scenarios. So here I just placed the demo scenario JSON. So we'll click reset to reload. And then we see the scenarios or the scenario appearing in the sidebar. And clicking it, we see the events presented in a table view. To run it, we click load scenario and start the simulation. After 10 seconds, the first line will turn green, indicating that the mass has been overridden to 5. And after 20 seconds, we'll see that the second line will turn green, indicating that the spring stiffness has been overridden. There. Having a look at the mass velocity in y direction, we see that at 10 seconds, the mass is reduced, so the spring force increases the velocity, and then after 20 seconds, the spring stiffness is increased, so the period of the oscillations increases as well. That concludes the features I have time to demonstrate in the Cosim demo application today. Note that the features I've shown and more is documented in the user guide available online. There's a link here in the top right to the user guide. I'll come back to these documentation pages later. And now let's move over to the command line interface. Here you see the Windows command prompt, and we are in the directory where I have downloaded the latest release of the Cosim command line interface. Running Cosim help gives us the built-in documentation. Here we see a set of subcommands that we can use. And one of them being run, which runs a simulation. So to learn more about a subcommand, you can use the help option on it. So Cosim run help brings up the documentation for the run command. It takes the path to the configuration as argument and runs the co-simulation. There's a list of options allowing for setting the duration of the simulation, specifying where you want the results, running scenarios, setting real-time factor, and more. To simulate our mass spring damper configuration, we'll write Cosim run, and then the path to where we have our config that we just looked at, and that is configurations tutorial. I'll use the V option, meaning verbose, so that we get the option, get information printed to the screen, and the D option, which means duration. So we'll simulate for 100 seconds. Here we got some output. The first part of the printouts are coming from the simulation models themselves. And after the models were instantiated, we see some info messages stating that some specific variables are being logged. This is because we still have the log config XML in our configuration directory. When we use the demo app, we specify that we wanted to log these specific variables instead of all the variables. At the end, we see the progression output that was printed during the actual simulation. So where are the results? If you don't specify anything else, the results will by default appear in the same directory as the Kosim executable. I have the Kosim executable right here. And from earlier, we will recognize the mass and spring CSV files. For the open the mass results, we see that these are still the X and Y coordinates, and the command line interface should also produce the same results, of course. Back to the command line. Let me show you a few more commands. We have the inspect command that will provide information about the model. Let's try to inspect the mass FMU. Kosim inspect, and it takes the path to the FMU. Configurations, tutorial, mass FMU. Thank you. The information presented here comes from the model description inside the FMU. We see the model name, description, author, and version, and all the variables are listed with the name, type, causality, and start values. This is a machine readable output and suitable for scripting. The last feature I will demonstrate is running simulation of a single model, which can be useful for exploration and debugging purposes. That is called runs a simulation with a single sub-simulator. Let's have a look at its documentation. It takes the FMU as the first argument, the path to the FMU, and then you can provide initial values as following arguments. In addition, you can use options for setting duration, step size, output file, and so on. Let's test it again with a mass FMU to run that model. Kosim run single. The path to our mass. There we go. And again, I'll use the V option so that we can see the printouts. And there the simulation is done. If you don't specify the output file, a model output CSV file will be generated. So it's right here. We can have a look. We did not provide any initial values for when running this mass model in a single mode, meaning that the mass now started with default position at x0, y0. And with run single, we simulated just the mass model, so it was not connected to the spring or damper. And as gravity is part of the mass model, it should now be free falling. And looking at these two columns that contains speed and y position, speed and position in the y direction, we see that the mass is actually falling downwards. So run single is a nice feature for testing and exploring models one by one. And with that, I'll leave the command line and move on to the configuration tool couple. order to stay within the allocated time, I will demonstrate couple using some screenshots. Here we see the user interface of a couple. And in the beginning, I introduced it as a graphical drag and drop configuration tool to create simulation setups. I will show how to create configurations from scratch. But first, let's see what our familiar mass spring damper system will look like in couple. We have the configuration complete that we have already looked at. So then you can just simply drag the OSP system structure file into its canvas. And couple loads the configuration, displays the simulation models and their interconnections using the OSP-IS variable groups. To simulate the system, we right-click the canvas and select Run Simulation. And the results can be visualized with a plotting feature. In this mass spring damper case, we started with a complete configuration, but couple targets to help with creating the configuration. So I will illustrate the process of doing just that. We start with a blank canvas and a set of FMUs that we want to connect into a co-simulation. These are just examples. And let's drag one of the FMUs into the canvas. This one was named Thruster Dynamics. And by double-clicking the simulation model, we get access to its properties. Here we'll see the FMI variables that this FMU has defined as inputs and outputs. And if we click variable groups, tab right here, we get access to a feature where I can build up the variable groups. We don't go into details of building these variable groups right now, but here I've created two variable groups in this case, the trust command and trust. Then I expose the variable groups as inputs and output on the simulation model. And I'm done with this specific simulation model. I can then right-click the configuration item in the navigator view on the left-hand side to export the configuration to XML files. Now we got the OSP model description file for this Thruster Dynamics FMU, which contains all the variable groups I created without having to write a single line of XML myself. In addition, we got the OSP system structure that will not contain any connections yet, as we just have one FMU so far. For the remaining process, I will drag in the remaining FMUs and create the needed variable groups and create the interconnections. And we'll end up with a configuration that looks like this. Using the export functionality now gives us the complete co-simulation configuration, and we are done. All right, so now I've demonstrated 3 different applications that uses libcosim. And I thought I also should show you a few lines of code to demonstrate how you can use libcosim to include it in your own application. If you're not familiar with C++, it really doesn't matter. I think you will be able to follow the steps anyway. In this example, we defined start time, stop time, and step size for the simulation. It will start at 0, simulate for 10 seconds, and use a step size of 100 milliseconds. Then we create a URI resolver, and we can use that to specify the file URIs to where the spring and mass FMUs are located on disk. Then we establish a system structure, and we add the models to the system structure, add entity, spring model, and name them spring and mass. Then we can connect variables from the two models programmatically. In this example, we connect variables. We connect the spring output force to the mass input force, and the mass output velocity to the spring input velocity, which finalizes the system structure in this example. To simulate the system, we create an execution. And here we tell the execution to start at our defined start time and to use a fixed step algorithm using the step size we defined in the beginning. On this line, we inject the system structure into the execution, and we are ready to simulate, which we do by telling the execution to simulate until the stop time. Here we built the system structure in code. The execution can also be created directly by loading the configuration file that specifies the simulation models and their interconnections. Here we see an overview of how the OSP software components build on each other. We have libcosim as the foundation, the C++ Co-simulation library, where all main features of the OSP software has been implemented. On top of libcosim, we have the C wrapper, libcosim C, and the Java wrapper, Cosim4J, for developers who want to use libcosim with other languages than C++. The dark blue boxes are the applications that you have seen demonstrated today. As the Kosim demo application and the command line application are open source, they are prime examples on how to use libcosim C and libcosim. The configuration tool couple use Kosim for running simulations, and the OSP validator to validate the configuration. And here we see the Co-simulation overview that Kristine presented in the beginning. And I think it can be useful to highlight where the OSP software tools come into play to help you create the system configuration. You can use couple. To validate your configuration, you use the validator, either standalone or within couple. To run simulation, you either use the demo application with a graphical user interface or the command line interface, or your own tool by embedding libcosim. To easily get started, you can use the Maritime reference models that includes plug-and-play setups ready for simulations. Please visit our project page at opensimulationplatform.com. Let me open it. Here you can learn more about the OSP interface specification. You get access to the specification document, the ontology, and the validator. You can further read about Co-simulation in general, find information about Maritime reference models and the use cases demonstrated in the project. The OSP software link takes you to the software documentation pages on GitHub. And here you find the documentation of all the OSP software components. Kosim, libCosim TC, targeting developers, the command line interface, and the demo application that we just demonstrated, the Java wrapper Kosim4j. All the reference models are listed here, and example configurations that makes use of these models are also documented. Then we have pages for getting started with the OSP validator and configuration tool couple. There is also a download section to get access to the latest releases. Note that documentation pages links to the source code on GitHub to the top right. So if I click this one, I will come to the libCosim repository on GitHub. If you experience bugs or want to suggest new features, please use the issues feature in GitHub. This is the list of already registered feature requests and bugs. So here you can click new issue to create a new one. If you are interested in contributing to the software, you are welcome to do so. Each of our repositories on GitHub has a contributing file with contributing guidelines that will give you the information you need. And don't hesitate in getting in touch by sending an email to contact@opensimulationplatform.com. So far, we've only looked at simple toy examples when demonstrating the OSP interface specification and the OSP software. To learn more about realistic use cases for what OSP can be used for, I will give the word to Kevin, who will tell us more about one of the use cases demonstrated in the OSP JIP.
Hello. Can everyone hear me?
Yes.
Yes, that's good. Yeah. Okay. My name is Kevin Koosup, and I was the OSP JIP use case 1 lead, and I'm a research scientist working in SINTEF Ocean, living in Trondheim. Okay. The main objective of the use cases in the JIP was to study the feasibility of the OSP software in various phases of lifetime of a vessel, design, commissioning, and operation. We also used the use cases to provide the user feedback to the development of the software. In the first use case, which I was responsible for, the main question we tried to answer was if co-simulation using OSP software is a useful tool for the system design in early stage. The question, in short, should we run a system simulation using OSP from day one? So we formulated the use case into a collaborative design study together with partners in the JIP. And the main goal of the design study is to find an optimized sizing of power system and battery energy storage system for hybrid ferry together with the optimal control of the system. The cost of function is the total cost of ownership, ideally. Why this use case? We wanted to explore the feasibility and benefit of using OSP in the early design stage, where you need to run a large number of simulations, build a system model with components from different parties, and apply model-based systems engineering and knowledge-based engineering. Let's take a look at a specific example. This plot comes from one of our simulations. trying to point out the. Okay, yeah, there you go. So here you see the battery is responsible for the propulsion power, which is this gray line. The battery is now responsible for giving the power to the propulsion power in the beginning until the gensets are ready for providing power. In addition, there is short power rush to accelerate the vessel, which is this large peak here. So peak shaving is happening. And as the propulsion load is going down to steady state, battery is being charged in order to maintain its state of charge. When SOC is at desired level, charging stops, and then all the powers are delivered by gensets only. And at the end of the journey, propulsion load drops and the vessel is on zero emission mode. There are lots of things happening in this short transit of this hybrid ferry. And it will be very difficult to tell whether this type of operation will really save fuel and reduce emissions at reasonable capital costs without running this dynamic simulation. So the system simulation is necessary even at this early stage. So we teamed up with many among JIP partners. I'm very proud that we had quite a large number of participants, and each of partners contribute to the use case with model, knowledge, ideas, and interesting discussions. And as a team, we defined our task as defining the system specifications, the building a design tool, running a system simulation, and thereby performing a design study. We spent some time together defining the system scope and structure, model fidelity, and interfaces. These were crucial steps before we go down into modeling activity. FMU models are actually developed by 5 participants and delivered to me so that system can be configured. As we discussed, to run a large number of simulations, as we needed to run a large number of simulations, we mostly use the quasi-steady state models while maintaining a crucial dynamic properties, such as vessel motion and propulsion load changes, and power balancing the power system. The system simulation typically runs at 30-40 times faster than real time, which is an ideal for the early design trials. And this system model can be further elaborated in the later design stage while keeping its structure to serve other needs such as design verification, hardware and loop testing, and virtual commissioning. Another main task in the use case was to develop an integrated design tool that embraces the design process with an intuitive UI and support for database. In order for the tool to be a collaborative tool, the tool is developed as a web application where many users can work simultaneously with the same source of FMU models or system models. You can see the design tool in action on YouTube by following this link. As a final remark, we have created a Python package that provides user interfaces to Cosim that just Levi introduced. So main functionalities are this can provide FMU management. You can configure a system scenario and loggings with a similar interface as you have seen on C++ in Python as well. And also you can deploy the files for simulation and run simulation and get results as data frame, which is more favorable data format in Python. There are examples using this PyCoSim, and you can simply install PyCoSim if you want to use it. Okay, then I'll give words to Thomas. No, actually, Thomas for the next use case, which is virtual commissioning.
Yes, hello. I think you need to end your presentation, Kevin, or no, I can override you, I think, yeah. Okay.
I'm doing it now.
Can you see my presentation now? Or rather now?
Yes.
It's good. My name is Thomas, and I'm a research and development engineer at Kongsberg, Maritime. And I will present to you the virtual commissioning demonstration case for OSP. So let's start by defining virtual commissioning. I like to think of it as something that's concerned with testing integration of software components. And then we typically mean some kind of control system connected to a simulator, providing some kind of input. And control system can run either natively on production hardware or in some kind of virtual environment, which is similar to what we know as either software in the loop or hardware in the loop testing. So why should you bother with virtual commissioning? I think there are many benefits to gain from this way of working. And one of them is you can test early. By testing early, then you extend your testing period and thereby increasing the probability of finding errors. And you also detect errors earlier in your process. This is the left shift that Kristine talked about, meaning that and when you uncover errors early, they are easier to fix and cheaper to fix. You can also run your control systems and simulators in a virtual environment, and you can even virtualize your hardware. Virtualizing your hardware removes the need for buying expensive equipment for testing or setting up sophisticated labs. And running everything in a virtual environment will often make it easier to set up network configurations or test things that cannot be as easily tested with physical hardware. And of course, we can do integration tests because even though your software components doesn't works individually, there might be issues when they are connected as part of a larger whole. So this is the question that this demonstration case wanted to answer. And I guess I can spoil it and say that the answer is yes, we can. But before we look at the results, let's take a look at the system that we commissioned in this demonstration case. The system is inspired by a vessel called OV Ryvingen, which is a real-life vessel owned by Kystverket. And the system consists of a vessel model delivered by DNV GL as an FMU, thrusters and sensor models from Kongsberg Maritime CM delivered as FMUs, a DP controller from Kongsberg Maritime running on native production hardware, and a PMS controller and thruster controller from Kongsberg running in a virtual environment. The network FMUs you see here are just network protocols wrapped in the FMI interface in order to communicate with the control systems. And everything is of course connected using Cosim, which controls both the connections and the synchronization. So can't go through the results here because I don't have time, but you can view the resulting videos on the OSP homepage. And I recommend you go and do that after the presentations, if you haven't already. I will finish off by talking about the benefits of using OSP-IS and Cosim for this demonstration case. A main benefit is that by thinking in terms of variable groups instead of individual connections, I can simplify interfaces and connect groups instead, leading to fewer connections. The type checking allows me to see if something is wrong before I run the simulation. And the interface specification allows me to speak a common language with other integrators and model developers. This, in turn, reduces the cognitive load, which makes me, as a person, as a human that can only think of a few things at a time, do fewer errors, which I think is an important part of this. Here are some of the essential functionalities of Cosim that I had to use. The real-time synchronization functionality in order to talk to a real-time control system. The OSP-IS configuration gave me the benefits of the previous slide. The web interface demonstrated by Levi enabled me to plot data, and the scenario engine, as was demonstrated. And you can also run distributed simulations with Cosim, which is essential when communicating between different control systems and platforms. So this concludes my brief introduction to the virtual commissioning demonstration case. I will now give the word to Kristine.
Yes, thank you. I don't know if you can see me or hear me. Yes,
I can see and hear you.
That's good. There's hope. So I say, do you want to continue? Yes. So let's hope something for the operational planning comes up on your screen now.
Yes.
Yep. Then I'll, the last use case, we had an OSP setup for planning crane operation, and we used the NTNU research vessel Gunnerus. We wanted to compare scenarios for instance, changing the setting of the crane, or if you change the environment, how will your DP performance be then? So we wanted to create the setup where you could do such simulations. And as FMUs for simulating DP operations were already available from previous projects, it also became a demonstration on how you can take someone else's FMU, how easy it is to export or to reuse it in with the OSP simulation software. So since a lot of you are from NTNU now, I also mentioned the specific projects where we took these FMUs from. It's VPROMA and TwinShip. And we also developed a new crane model because the knucklebomb crane here is new for Gunnerus, and extended the hull. There's a new hull model as well since the hull was extended. But other than that, it's reused from previous projects. Another important factor when doing operational planning is that a lot of the JIP partners wanted to see 3D visualization. So we found a way to reuse the setup and export it to a provider of visualization software. So for the JIP case study as such, we had limited time for exploration of systematics of exploration of these scenarios, but the vessel is studied further, both in R&D projects in NTNU in Ålesund and in Trondheim, and we'll focus on how one could utilize data from the vessel in operation and combine it with the simulation models on the OSP, which I think is very interesting. So how does it look like, the simulation setup? We had 13 different FMUs, and some of them, due to runtime requirements, needed to be run distributedly with the FMU proxy tool that might have been introduced today. And we are using a simple scenario management to run the scenario file in the Kosim demo app. And as I said, we were exporting it with using the Cosim 4J and exporting it to the offshore simulation center that has made the 3D visualization. The video of that is available on our webpage. So the main thing to talk about here, as we have limited time, is that we all know that there is not one connection between the vessel, for instance, and the crane. So this is how it looked like when receiving the FMUs from 20Sim and from the previous project. The vessel model, I believe, is in the VSIM. And you can see there's a lot of variables that you need to interpret how you should connect between the models. And either you need to do this in a graphical tool to connect it if you want to reuse it, or you need to write it in XML code. So the magic happens when you apply OSP-IS and also can use the tool couple. You can simplify the connections between the vessel FMU and the crane. And the way you do that is as introduced to define variable groups with OSP-IS for each of the models. That will and also enable you to make a more simplified model description file for each of them and the OSP system structure. So it was quite time consuming to do this for the first time, having the models delivered from previous projects and do this variable grouping and also define how the connections should look like. But if you want to reuse the vessel FMU later in a different setting, or if you want to swap the crane with a different crane, this work should be much easier and less error prone when you have less connections to work with. So to conclude on the 3 use cases, we tested most of the OSP features with success, but what did we actually learn from using FMUs? One of the benefits is that we see that it's very beneficial when you want to collaborate between different domains, as we all use dedicated tools or specialized tools. And it's also when you receive models from different providers, it's a higher chance of uncovering emergent properties. And we also, throughout the project, 3-year project, we see that there's an increased support of tools using that enables you to do FMI export, or that supports the FMI standard. But we also know that generating FMUs for reuse requires some training. The various simulation tools have various degree of support for this, and also the structure of your original model will decide a little bit how easy it is to export it. If you have a very modular setup in the first place, it's easy. But if you have one of these spaghetti type of models, it's less efficient. So it will require some training to do this efficiently. And we also, it's difficult to, might be challenging to debug. You're not supposed to know what's going on inside the FMU, but you should be able to have clear and standardized interfaces and documentation of the intended model functionality. That will simplify this debugging. And also it would be preferred to have tests to verify the functionality and performance of a model, that it is according to its intended use before you start configuring the whole system simulation, because then it can be very difficult to debug when you have everything connected. So the co-simulation benefits we saw, we see that models can easily be delivered and accessed by many stakeholders. We see also that it's possible to reuse models for different stages of a vessel life cycle. And we saw increased willingness to share between the system providers when they could share them as FMUs, and so to protect the IPR. And we also see a huge benefit that you can update when you have a modular setup. It's easier to update the model or the overall system model to reflect the actual status of a vessel when you go into operation, when you do modification, updates, whatever. So the value, as we see, provided by the OSP from the use cases is that both the FMI and the OSP-IS building on top enable efficient sharing and reuse of models. And particularly the open source facilitate development of new applications, as for instance Kevin did, and linking to external tools or customized software. And this because it is extendable, flexible, and transparent to work with. So I think this was my last slide. Yes, then I hope you get some impression on how it was to actually use the software. Thanks. And then I don't know if you have concluding remarks, Lars.
Yes, thank you, Kristine. We're now at the end of part 1 of the OSP technical launch. I would like to thank all of our speakers for their nice presentations, and I would like to thank you in the audience for sticking with us for these 2.5 hours. I hope you enjoyed it, that you learned something, and that you're all eager to join us in the development of the open simulation platform into an entire model sharing ecosystem for the maritime industry. As these last few speakers have shown, the OSP is ready to use for real industrial use cases. However, as you may have noticed from the presentations before those, it is by no means complete, and non-technical users will have a hard time using it the way it is today. We in the OSP team, we will keep developing it, and we will build our tools, our models, and our services on top of it. But we need you in the community as well to integrate the OSP into your own software and your own workflows. For example, a ship designer would not use the OSP software directly, but a very powerful ship design software can be built on top of it, as demonstrated by, for example, Kevin earlier. Therefore, I hope that you, I hope that you will keep engaging with us through the various channels that Levi mentioned, where opensimulationplatform.com is the central hub. Open Simulation Platform in one word, without dashes. Regarding this webinar, if you have any feedback for us with regards to the webinar, please feel free to send it to me by email. You all have my email address. We'll probably have events like this in the future, and we're keen to improve wherever we can. And on that note, I close this webinar, and I will see some of you again for parts 2 to 3 in a short while. Oh, sorry, just before we close, I see we got the question in the chat here. Q&As. We may have announced that there would be a Q&A session at the end of this part 1. We elected to do that using Zoom's Q&A feature instead. And also some of you have received, or some of you were able to secure seats in a limited attendance Q&A session later today, and those of you have gotten emails. So I'm sorry if that wasn't clear, but you can always feel free to contact us by email or post questions on GitHub and so on. And with that, I close this webinar and hope to see as many of you as possible again in the future.